Hi, this is video 3 on random variables. In this video, we're talking about joint probability distribution function. In the previous video, we introduced probability distribution function for a given random variable. So now consider two random variables, and in fact, we have seen these before in our experiment of tossing a coin 3 times, x and y, right? So x was number of heads, y was matching tosses, right? So now the pair x and y together is a joint random variable, right? So essentially using both an x and y, right, we can define events, which is why we call this a joint random variable x and y. Again, as before with a single random variable, we can again define event probabilities that will be the sum of these outcome probabilities. But it's just that for all, essentially for all values that x can take and for all values y can take, we can define different scenarios, and hence this is essentially a joint random variable. For example, like maybe let me define that first and then look at an example. So for every possibility of x equals x, like this x can take like all possible values, and y equals y, we can compute the probability x equals x, y equals y. This is how we denote this joint random variable. And these probabilities together will constitute the joint probability distribution function for x and y, right? So unlike the previous example when we were interested only in this, now we are interested in the joint probability distribution of x and y. And this is, sorry, this has to be x, and these are lowercase x and lowercase y inside. These are uppercase, these are lowercase. Equals the probability for all possible values of x and all possible values of y. Right, so this is the definition of joint PDF. Let's look at some examples to better understand. For example, let's say we want to find, for the same experiment, let's say I want to find y equals 1 and x plus y less than equal to 2. Right? So what is that situation when x plus y is either 2 or less than 2? So it has to be either 2 or 1 or 0, and y is 1, right? So one way of looking at it is that I can go and read off from my tabular data that I have here, here. And I can simply go and add these outcome probabilities and then see where these overlap, right? Or I can just find the probability of this, which is 1/8, and the probability of this, and then just like see the overlap, right? And the overlap actually happens only at this one point when y is 1, right? So the probability of the joint probability of these two random variables is 1/8. Now we can also find a little more complex probabilities. For example, what is the probability of y equals 1 given x plus y is less than equal to 2? Now, from our knowledge of conditional probability, we know that this can be computed by finding this x plus y less than equals 2, right? Divided by the probability of x plus y less than equal to, right? This is from the definition of conditional probability. I already computed this thing, so I know that the numerator here is 1/8. Now I need to compute this, right? Probability that when x plus y is less than or equal to 2. Let's go and check when that's true, right? So I'm looking at x plus y less than equal to 2. Obviously this is not true, but this is true, right? 1, 2, this is also true. 3, 4, 5, 6, 7, right? So out of the 8 cases, 7 of them, for 7 of them, this holds true, right? So x plus y less than 2 is 7/8, right? So I substitute that here, and the probability that y equals 1 given x plus y less than equal to 2 is 1/7. Right, so these are like some simple examples demonstrating when and why can we need the joint probabilities of these two random variables. So let's go back to the joint probability distribution function, which we just defined in the previous slide, and then look at it in how can we organize it in tabular form, right? So the joint probability distribution function in tabular form looks something like this. And this is for the same experiment, right? So look, for x, the random variable x, we have all these possible values of small x. For y, the random variable y, we have all these possible values for y, right? And like each box in this table represents x and y. Now notice, when the number of heads is 0 and y is 0, what is the probability of this event? This is what these are representing. So the probability of that event, let's go back and check. When x is 0, no heads. So when x is 0 is 1/8, and when y is also 0, um, so there are multiple, but there is no and, right? These two never overlap, right? So the probability of these two events jointly is 0, right? Similarly, what happens when y is 0 and x is 1? Are there any overlaps? Let's go and check, right? So when y is 0, so all these y's are 0, and my x is 1. So well, 3 overlaps happen here, here, and here, right? And we know that each outcome is equally likely, so the probability is 3/8, which is exactly what we're getting here. Right, similarly, you can check for other boxes. It's essentially representing an overlap of the row and the column, right? So that's one. So each entry in this table, which is the joint PDF table, represents this. Now, if we look only at the row sums, right, the sum of the rows, if you look at the row sums, you can check that the sum for the first row is 3/4. Now this represents something that we call marginals, right? So that's joint, and these are marginals. So in a representation of joint PDF, something like probability of the random variable y over all possible values of y is a marginal, right? And these row sums are the marginal for y. So here, as you can see, this is the sum of all these here when y is 0, right? Similarly, this here is the sum for all of the other possible values of x when y is 1, right? And if we add these, we'll get 1, which obviously is true because the sum or the total probability of all possible events has to be equal to 1. So similarly, we can look at the column sums here. Column sums represent the marginal for x, right? Because look at this column for x equals 0, all the possible values of y, right? Which is why we have this summation here. Similarly, we have this summation here for the marginal for y, right? So this is again marginal probability for x. We can also derive this marginal probability using our idea of law of total probability. So for example, here, when you're looking at row sums, you are essentially calculating the probability of y for all given values of x. Or in case of column sums, you're calculating the probability of x for all given values of y, right? So using the law of total probability, this can be derived. But it's important to understand that the marginal probability given this joint PDF pxy is denoted by the sum of all the values that this y can take over this joint PDF. Okay, let's look at maybe another example, or independent random variables first, right? So just like we define the idea of independence in general for events, we can define the idea of independent random variables which actually stems from the idea of joint probability distribution, right? So if there are random variables x and y on a given sample space S, they're said to be independent if the joint probability distribution function is equal to the probability of x, marginal of x times the marginal of y. If this relationship exists, then the random variables x and y are independent. So this is the test for checking whether these are independent or not, given some joint probability distribution function. Um, let's look at an example to demonstrate how we can see whether two random variables are independent or not. Okay, so two dice are rolled. X1 is the number appearing on the first die, X2 is the number appearing on the second, right? So what we have to prove is X1 and X. Now notice X is not X2, X is the sum of X1 and X2. And we have to prove that X1 and X are not independent, right? So the way I am trying to prove this is by using a counter example. Okay. Let's assume I'm trying to calculate the probability of X1 for 1, right? So I know that each outcome is equally likely for X1, number appearing on the first die. So the probability of X1 equals 1 is 1/6 out of all 6 possible values, right? Now, let me compute the probability of X equals, let's say, 12, right? Now, in order to get 12, I must get at least like 6 and 6 on both X1 and X2, right? So the probability of X equals 12 is 1 over 36, because this is just one of all the possible scenarios that are possible when two dice are rolled. Now, let me go and find out the probability of X1 equals 1 and the probability of X equals 12, right? So when do they overlap? Sorry, I shouldn't have written probability here. Let me get, okay, yeah. So when do these overlap? These can never actually overlap, because if I'm getting x1 equals 1, no matter what value I get for x2, x will never be 12, right? So the joint probability of both of them is 0, right? So I can actually prove that this probability of this and this, which is essentially the joint probability of x1 comma x, is not equal to the probability of x1 times the probability of x, right? So using this counter example, I can prove that x1 and x are not independent, right? So this is what I wanted to prove. X1 and x are not independent, right? So then again, going back to our definition, this is the expression that we either need to prove or disprove in order to find out whether two random variables are independent or dependent. Okay, so with this, I end this video. In the next video, I'll talk about CDF or cumulative distribution function.